At least the way I taught this, there are a couple ways you can solve this. The way I taught this was to get all the denominators to be the exact same thing. That means this would need an x over x. This would need an x over x. This little guy right here needs an x plus 2 over x plus 2. So then you solve the equation that's left over in the numerator. After all the denominators are the same, you're going to have 2x plus 3x plus 6 equals negative x squared. This would be the equation left over in the numerator. If you get this equal to 0, you're going to have x squared plus 5x plus 6 is equal to 0. Factors in x plus 2, x plus 3 equals 0. Possible solutions are x equals negative 2, x equals negative 3. What did you guys say about negative 2? No. It makes the denominator equal 0. So the only answer is x equals negative 3. Okay, again, the way I did that was to get all denominators the same. Once that was the case, I solved what was left in the numerator. Okay. Question 2. There was a little typo. That was supposed to be a t right there, not an x. Anyway, this function right here represents an upside-down parabola. When they're asking for the maximum height and how long it takes, all that is the vertex. So there's a vertex formula. It's the opposite of b over 2a. That's the vertex formula. So that would be negative 32 divided by 2 times a. That's another negative 32. So that equals 1. This formula gives you the x value of the vertex. So we know that there's a 1 right there. How do we find the other value? We plug it in. So if you plug in a 1 for t, you get negative 16 plus 32, which is 16. 16 plus 100 is 116. So that's the vertex. How do we interpret that, though? What does it mean?
Which one is which? The one is x, or in this case, it's not really x, it's t. So after 1 second, it is 116 feet.
That doesn't take into account the guy's height or anything. It's just after 1 second, 116 feet. 116 feet high. Now, let's talk about other ways. You don't have to use the vertex formula. Anybody tried a different way? You could graph it and find the vertex on the graph. All this would be is an upside down parabola like this. So you could find the vertex that way. You could put it in vertex form by completing the square. What's that? Well, that's essentially what we did, is found the vertex of the upside down parabola.
Well, I know I'm saying you just have to use the vertex formula, and that's all you have to do.
Yep. Okay, question 3. Again, this didn't need to be there. You don't describe end behavior with interval notation. So anyway, the factors give you zeros. The multiplicity of the factors tell you whether it crosses or bounces. So we have a 0 at 3. We have a 0 at negative 3. We have another 0 at negative 1. Other thing you need to consider is the type of polynomial. This is a 4th degree because you have 4 factors, 1, 2, 3, 4. So that means the end behavior looks like this. End behavior is traveling in the same direction on a 4th degree polynomial. So what you got to figure out then is what's the behavior as the graph approaches each 0. What happens here at negative 3? Bounces? Okay. Now, how high up does it go before it comes back down? It goes how high? Oh, I thought you said 45. It goes up to 5?
No, I got hold on. It's 5. It's 5.
If you plug in a negative 2 for all the x's, you'd be able to figure out how high it goes. Did anybody do that? Anyway, it goes up to 5. Then it comes down. What happens at negative 1? Crosses through. Other thing we're missing here, you guys, we're missing another thing. We have the x-intercepts. What are we missing? We're missing the y-intercepts. If you let all the x's equal 0, That'll give you the y-intercept. This is negative 3
Negative 27.
times 9 times 1. It's negative 27. So the graph goes all the way down to negative 27. Then it comes back up like that. Okay? Guys, we got to stay focused here. The end behavior was really the important part of this question. How do you describe this piece of the graph right here? What is x approaching? As a point travels along this piece of the graph, what is happening to all the x values? X is approaching infinity. X is getting larger and larger, right? Corresponding to that, what is y approaching? Infinity. So that's one piece of the end behavior. How would we describe this other side over here? As x approaches negative infinity, y approaches infinity. That's what it means by describing end behavior. Okay. Question 4. Find a polynomial with real coefficients. This is what you need to pay attention to here. Real coefficients. That's degree 4 zeros, blah, 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 blah. So first of all, it's x minus 1, x plus 2, and then x minus 3i. What are we missing? X plus 3i. Now, this piece here, real coefficients, that means you have to multiply it all out and write it as a polynomial that doesn't have any i's in it. So you got to multiply this all together. For sake of time, I'm not going to go through the whole process. You guys know what to do, right? This would turn out to be p of x equals x to the 4th plus x to the 3rd plus 7x squared plus 9x minus 18. That's what it would look like all multiplied out. Okay? Well, page 2. We got to do all 4 of these for each one of those questions, so we got to hustle. Part 1 says the rational zeros theorem. That's just the p's and q's, right? Where do they come from, the p's and q's? The 6 and the 1. P divided by q in this case. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, in the interest of time, what you would have to do is just choose one and test it to see if it works. I'm going to choose positive 1. Negative 3? 1 works as well. But you guys, listen, I can see a potential for a mistake. What's missing right here? The x squared terms. You have to have 1, 0, negative 7, and then a 6. Bring down the 1, multiply, add, multiply, multiply. We get a 0 right there. So what that means is p of x now equals x minus 1, and then the leftover polynomial is x squared plus x minus 6. What's so nice about that leftover polynomial? The factors. So it's x minus 1, x plus 3, x minus 2. So we've got fully factored. Now we can state the zeros. The zeros are 1, negative 3, and 2. What else does it say to do? All right, graph. So a 0, 1, 2, and a negative 3. Since this is a third degree polynomial, the end behavior is like this and like that. We're running, what's the y-intercept? Okay, just for sake of time, you'd have to be a little more exact than this, but it's going to come out like this, cross through. They all cross through because none of them have multiplicity. Then it asks for the end behavior. So how would you describe this end behavior right here? X goes to infinity, y goes to infinity. This one here, x goes to negative infinity, y goes to negative infinity. That's the end behavior. All right, moving on. Sorry, I know I'm going real quick. I want to try to get this one done. The next review has what does the next review have? All of the trig stuff, parametric equations, the polar equations. It's on Friday. It's got conics, the hyperbolas, the ellipses. There's a lot on that we need to cover. So anyway, this one here, the P and the Q, will be plus or minus 1, plus or minus 3. Which one worked? Negative 1? Okay, so we have 1, negative 2, negative 2, negative 2, negative 3. Let's see.
Negative 3 works.
Negative 3 works as well. So far we have partially factored x plus 1. And then we have this reduced polynomial, x to the third minus 3x squared plus x minus 3. Anybody else find another one that works? Positive 3? Okay, so I'm going to use positive 3, but I'm going to test it on this reduced polynomial here. Okay, so what we have now is x plus 1, x minus 3, and then we have this reduced polynomial, x squared plus 1. Now, that doesn't factor, x squared plus 1. So we have to find the zeros another way, either quadratic formula. This one, I guess you don't have to use the quadratic formula for. How can we find the zeros from this? Set it equal to 0, subtract 1 square root. So you're going to have x squared equals negative 1, which means x equals plus or minus I. Now just keep in mind, you guys, these are just sample questions. What if...
You got to think ahead on Friday. What if the one question had a term in the middle, like x squared plus 7x plus 1? There you'd have to use the quadratic formula to find the other zeros.
This one you didn't have to. But anyway, fully factored. Does it ask for fully factored?
Yeah.
All right, anyway, it'd be x minus I and x plus I. Now, you guys, you need to listen carefully. This does have 4 factors, but it only has 2 real zeros. These 2 factors right here, x minus I, x plus I, they don't give you zeros on the graph. So the only x-intercepts we're going to have come from there. So on your graph, we have a 0 at negative 1 and a negative 3. The y-intercept is negative 3. Since this is a 4th degree polynomial?
No, it's positive 3.
Positive 3. You're right. We have one over here. Since this is a 4th degree, the end behaviors are traveling in the same direction. So it comes down. It may have a little bounce right there or something like that. But anyway, that's essentially what the graph looks like.
Okay.
And then the end behavior, as x approaches infinity here, y approaches infinity. And then over here, what would you say? X approaches what? Negative infinity, but y approaches positive infinity. That's how you would describe the end behavior. Okay. This one, I would write it in factored form. X plus 3, x plus 5 over, let's see, does this one factor x minus 5 and x minus 1? The denominator is where you get what? What do you get from the denominator? The vertical asymptotes. So we have one a positive 1 and one a positive 5. We have vertical asymptotes at 1 and 5. What about the horizontal asymptote? There were 3 cases. If they're the same degree, then you just divide their leading coefficients. So in this case, it would be 1 divided by 1. But that's just one of the cases. You guys have to anticipate you might have one of the other cases on the test. What could potentially happen? If the bottom were higher, it'd be 0. The horizontal asymptote would be 0. If the top were higher, you'd have no horizontal asymptote. So those are the things you need to remember about this. Now, the numerator. What does that give you? The x-intercepts. So we have an x-intercept here and another one here. Okay. It's a little odd. Now what do we do? So what about this? There's no x-intercepts here. It has to be up here like that. Because there are no... Do you guys understand that? There are no x-intercepts over here. What about the middle piece? If you plug in points, it's going to look like that. How come it can't be turned down? There's no x-intercepts here. It's not going to cross through the x-axis if there's no x-intercepts. It would eventually cross through the x-axis if it was pointing down.
No, it'd be below x-axis.
Oh, it could. Oh, you mean all the way down like this? Actually, it might be. Let's check. Plug in a 2. If we get a 2, we get a positive up here. If we plug in a 2, we get... Well, no, this is going to be negative. That's going to be positive. Negative times a positive is a negative. So overall, it's... So yeah, it's down here. Yeah, good catch. Okay, you guys, this one right here is a little weird. What happens over here? Oh, we missed one thing. We forgot the Y-intercept. How do we figure out the Y-intercept? Let all the x's equal 0. So it'd be 15 divided by 5, which is 3.
I got a problem.
This is kind of a peculiar one here.
Is it going to slip through one of the dotted line cracks?
Okay, you guys, yes or no, can a graph cross through a vertical asymptote? No. Yes or no, can a graph cross through a horizontal asymptote? Yeah, it can. Okay? So the graph has to be coming through like this. Okay? Where does it go from here? Doesn't it have to eventually cross through this?
-4 is -1, so...
Okay, so it comes down here, and then where does it go? It has to go back up, and then it levels out and follows that asymptote. The horizontal asymptotes are there to describe the behavior as x approaches infinity here. Towards the origin, it can cross through the horizontal asymptote, but eventually it's going to have to level out and follow it. So, it's kind of a weird one. Just plot points. Okay, moving on. Just for sake of time, we're gonna skip back to this one later. This one's easy. These next couple ones we can go through pretty quick. Number 8. What are we getting on number 8? What cancels a log base 81? A base of 81 on both sides. So you have 3 is equal to 81 to the 1/4. That's all you gotta do. It just says write it in exponential form. That's exponential form. Question 9. Same type of thing. How do you cancel the base of e? So you use a natural log on both sides, and you get x equals natural log of 6. That's all you have to do. Okay. Find the inverse. If we have f of x equals the natural log of x plus 4. The inverse. How do we find the inverse? Not just of this, but of any function. Switch x and y. Good. So we're going to have x is equal to the natural log of f of x plus 4. Now, f of x is inside that little natural log. Somehow we got to cancel that out so we can get to the f of x. How do you cancel natural log? Base of e on both sides. Okay. So the e cancels the natural log. What we have now is e to the x is equal to f of x plus 4. Now what? Subtract 4, we have e to the x minus 4 is equal to, now you got to change the notation here since this is now an inverse. It's f to negative 1 of x. So that's the inverse. Okay? So that's the first part of the question. Now it says state the domain and range of both the original function and the inverse function. Let's start with the original function. Okay? You guys need to listen carefully. With logarithm functions, you cannot take the logarithm of negative values or 0. You guys follow? So we're taking the logarithm of x plus 4. That means x plus 4 has to be greater than what? It has to be greater than 0. Otherwise, we couldn't take the logarithm of it. You cannot take the logarithm of negative values or 0. So the domain has to be x plus 4 is greater than 0. Well, what's the domain then? X is greater than negative 4, so that's parenthesis negative 4 to infinity. That's the domain for f of x. The range for logarithm functions. Yep. The range for logarithm functions is all real numbers. This is for f of x, you guys, right here. For the inverse, do you guys hear that? If we switch the place of x and y to find inverses, then don't we have to switch the domain and range? Because that's all domain and range is x and y's. So you're going to switch these. For f negative 1 of x, the range is going to be all real, or the domain is going to be all real numbers. The range is going to be negative 4 to infinity. So domain is all real numbers. The range is negative 4 to infinity. That's what we did. Yep. To find the domain range of an inverse, you take the opposite of the domain and range of the original function. Okay. Well, let's do as many of these as we can. We got to get this exponent by itself. How do we do that? What kind of logarithm here? I would do a log base 2. So log base 2 of 27 is equal to 3x minus 1. Now what? Add 1 and then divide by 3. So log base 2 of 27 plus 1 all over 3 is equal to x. Now, your test is going to have two parts, a no calculator part and a calculator part. If this were a question on the no calculator part, this would be your answer. You guys follow? Because you couldn't figure this out without a calculator. If this were, however, on the calculator part, you'd have to type this into your calculator to figure out the decimal approximation. Okay, now, depends on what kind of calculator you have. You're going to need to get one for next time. If you have one of these graphing calculators that does logs with different bases, you can use that feature. So log base 2 of 27, then add 1, then divide that by 3. You get 1.91.